So let us welcome to this lecture on the topic of flip-flop conversion algorithm. So in this lecture we will learn how to convert one flip-flop to another flip-flop. So we know the flip-flop is a part of a sequential circuit. And what is sequential circuit? Sequential circuit is actually not depends on the present input. It is also depends on the previous input of the system. Okay, so flip-flop is we are going to learn means the conversion process of one flip-flop to another flip-flop. So let us move for the what are the algorithms are involved for the conversion process. So in this slide I just given the complete algorithm of the conversion process from one flip-flop to another flip-flop. So suppose that we want to convert X flip-flop to Y flip-flop. So what are the requirement? In the step 1, the requirement is we need X flip-flop excitation table, and on the right hand side we need one truth table for the Y flip-flop. So if you get these two table, excitation table and truth table, then we have to merge these two table. Okay, then we get a merge table. Okay, we get a merge table in step number 2. Okay, after that in step number 3, from this merge table, okay, we have to apply the k map. Okay, if we have to apply the k map and we try to find out the boolean expression of a y, okay, from the k map. Okay, then from the y expression we try to find out the logical gates are involved, how logical gates are involved to design a y. Okay, then this logical design is useful to convert the circuit. Okay, now I give you some example. Suppose that we get some boolean expression. Suppose that y is equal to a plus b bar c. Okay, so there is some in flip-flop. This is X flip-flop and this is a 2 output Q and Q and bar. Okay, so we need here one design to change the input X. So here there is some input A, B and C, and from this expression, okay, from this expression or this block generate output Y. So if we connect this Y output to X, that means this complete design, okay, this complete design is changed into change into Y flip-flop. The question is how to design this block. So the design of this block is very simple based on this boolean expression. So from this boolean expression we know there is a AND gate, okay, and one B input and one is C input. Okay, we need one OR gate, and we need the input A. Okay, so this, if we get this output Y, so if you connect with the X flip-flop, okay, if you connect this X flip-flop, that means now this design is changed into Y flip-flop, because this Y flip-flop is dealing, okay, this Y input and this is the 2 output of this flip-flop. Okay, now let us more clear picture about we take one example, then we get a more clear picture about this conversion process of the flip-flop. Suppose that this is a problem, means we want to change the D flip-flop to SR flip-flop. Okay, so now we just see this algorithm. This is very helpful for the conversion process. So in the left hand side the X flip-flop, so suppose that this is the X flip-flop, D flip-flop is X. So for X flip-flop we need one excitation table. Okay, what is excitation table? Is actually excitation table denotes the what is your present and next state, and based on the present and next state we have to identify the input condition. Okay, so here we know the present and next state. So Q1 denotes the present state and Qn plus 1 denotes the next state. So if the present and next state both are 0 0, the input value is 0. In case of present and next state is 0 1, your D value is 1. And in case of 1 and 0, the D value is 0. In case of 1 1, the D value is 1. Okay, we get this excitation table. But we need one more table. Okay, we need one more table for Y flip-flop. So Y flip-flop is SR flip-flop. So we need one two table for SR flip-flop. Okay, so this is the two table for SR flip-flop. Okay, in the SR flip-flop, okay, we are going to find out the next state. Okay, so suppose that if the S and R both value is 0 0, that means the next state is same as previous input. Okay, if you observe here, the present and next state is same, there is no change. Okay, now if the input is 0 and 1, if S is 0, R is 1, that means the output is reset. So in this case you get next state 0 because the output is reset. Your reset condition denotes 0. Okay, now in case of S is 1 and R is 0, that means this condition is known as a set state. So this time your output is 1. Okay, this time your output is 1 and set condition is known as a 1. But very interesting case, if both S and R is 1, so at that time we do not know what is next state. Okay, whatever your present state, we do not know what is the next state, that is the unpredicted state. Okay, or invalid case. Okay, we get two table. One is one table is truth table, another table is excitation table. Now we are going to merge these two table. Okay, so here we write first this SR flip-flop truth table, and from this truth table we have to generate the D. Okay, so here we observe the Qn plus 1 value. So suppose that both are 0 0, so in this case the D output is 0. So here we write 0. In case of 1 1, the D value is 1. Now in case of 1 1, the D value is 1. So in case of 0 0, your D value is 0. In case of 1 0, your D value is 0. Okay, in case of 1 1, in case of 0 1, the D value is 1. Okay, in case of 0 1, your D value is 1. Okay, but this two condition is a invalid condition because we do not know what is Qn plus 1. So this is the merge table. Now this merge table is very helpful to find out the D expression. So this is the these are the D value, and this value to be located in the K map. So this is a K map. This is a K map for merge table. So the input is S, another is R and Qn. So how many ones here? In case of 1 4 and 5. Okay, 1 4 and 5. Okay, so we just locate here 1, and don't care condition is on 6th and 7th case. So we write X. Don't care denotes the X. So we just form a combination or pairing here. So here we get two pairing. One pair, from this pairing we generate R bar Qn. From this complete pairing we get S. Now we get this expression D value. D value is S plus R bar Qn. Now we are going to convert D flip-flop to SR flip-flop. That means your input is SR, and this D value we know. Now what is the D value? By this Boolean expression. So what is this design is actually? This design is identified by this Boolean expression. So if you observe this Boolean expression very carefully, so in this expression we need one AND gate and also plus one NOT gate. Okay, if you combine these two expression, we need one OR gate also. Okay, we need one OR gate also. So here we taken one AND gate. Okay, here we apply R input, and here we get R bar, and another input is Q. So we just connect the wire. Okay, we just connect the wire and we get Q here. So this AND gate generate R bar Q. Okay, and this is the S input. So if we use OR gate, we get D value. Now D value is changed here. D value is changed with this Boolean expression. Okay, so this is a complete conversion process from D flip-flop to SR flip-flop. Okay, now one more example now we take, then you have more understanding about this conversion process algorithm. Okay, so the next situation is we want to change the D flip-flop to JK flip-flop. Okay, so suppose that D flip-flop is a X and JK flip-flop is Y. So please look on this algorithm, that is very helpful for the conversion process. So we need X flip-flop is D, so that means we need one excitation table for D flip-flop. Okay, so excitation table means the present and next state. We have to identify what are the inputs. Okay, what are the inputs? So input is 0 1 0 1. Okay, this is the condition of the, this is a combination, because input is 2, that means the combination is 2 to power 2. The 4 combination we have to form, and we have to identify the input. So we get excitation table. Now for Y flip-flop, means Y flip-flop is JK, so we need one truth table for JK flip-flop. So this is a table for JK flip-flop. Okay, so in the truth table, here we taken all the combination and we are looking what are the next state. Okay, we are looking what are the next state. So in third step, we are going to merge the truth. We are going to merge the truth table and also the excitation table of D flip-flop. Okay, so how to merge excitation table? So first thing, you write this truth table JK Q and Qn plus 1. So Qn denotes your present state and Qn plus 1 denotes the next state. So in 0 0 case, if you look here in the excitation table, in 0 0 case your D input value is 0. So here we get 0. Now if you look here, this condition is 1 1. So in this case your D value is 1, so we have to write here 1. Again in case of 0 0, your D value is 0. Okay, now in case of 1 0, what is the D value? 0. So we have to write here. Okay, so same thing here, if in case of 0 1, the D value is 1, so we have to write here. Okay, in case of 1 1, your D value is 1. In case of 0 1, the D value is 1. In case of 1 0, the D value is 0. So this is a merge table. Okay, so after that we have to apply the K map. So that is very simple, because here the three variables are there. One is J, another is K and Qn. So we take this combination, and now here 0 0 0 1 1 1 and 1 0. Okay, so we just find out the min terms here from this here in case of min term 1 4 5 6. So in that case 1 4 5 6 the output is 1. So 1 4 5 6. Okay, 1 4 5 6. Okay, then we have to form a combination. This is one combination, and here another combination. From this combination we get K bar Qn. From this combination we get J Qn bar. So ultimately you get D input is J Qn bar plus K bar Qn. Okay, so now we have to implement this function by logic diagram. Okay, so this is my D flip-flop. I want to change this D flip-flop to JK flip-flop. So this is a two output Q and bar. Okay, just look here. What is this first function? JQN bar. That means we need one AND gate, and we have to apply the input J. Another input is QN bar. So that means we have to take one wire here. Okay, we have to take one wire here and you just connect here. So this AND gate produce JQN bar. Okay, so the first function we have implemented by AND gate, and the second function is also also to be implemented by AND gate. So this time the input is K bar. That means we use one NOT gate. This is K, and now another input is Q. So that means we have to take one wire here and we have to connect here. Okay, we get K bar QN. Then we use one OR gate. Okay, so OR gate produce the D value. Okay, OR gate produce a D value. This have to be connect here. Okay, now this design is changed to JK flip-flop. Okay, now we have successfully converted D flip-flop to JK flip-flop. So I think you get a clear picture about the conversion process, how to convert one flip-flop to another flip-flop. So please remember this algorithm for the conversion process. Okay, now we come to some objective or some competitive exam questions to understand about the sequential circuits. So in the first question, we just read the first question. The next state in a sequential circuit is a function of. So the first option is present state, next option is next state, and C option is both present state and next state. Okay, so now we know very well in the sequential circuit not depend on the present input, but also depend on the previous input. So that means this C option is correct. Okay, so let us move to the next question. The speed of the sequential circuit comparative with combinational circuits. So this question is asking which circuit is more fast. Okay, which circuit is more. So sequential circuit is definitely not fast, because here there is a feedback connection, and also the output is depends on your present input and also the previous input. So this is a very slow. Now let us move to the third question. The next state of flip-flop. Okay, so the next state of flip-flop is same as input. We know the truth table of D flip-flop. Okay, the next state is same as the input. So the last question, the characteristics equation of SR flip-flop. Okay, so characteristics equation come from the truth table of SR flip-flop. Okay, okay, so in the characteristics equation, if we apply the K map, so we get this expression, that is S plus R bar Q. So this C option is correct. Okay, this C option is correct. So I hope you understand this flip-flop conversion process. So thank you very much.